Welcome to our next video on dividing polynomials. In this one, we're going to look at the remainder, how to use the remainder, and the factor theorems that will help us in finding these zeros and being able to factor polynomials. Okay, so again, we'll start off with just some basic uh, definition. In this case, it's the remainder theorem. It just tells us that if we're dealing with a polynomial, f of x, and if it's divided by a linear term, remember before we were only dividing by these linear terms, x minus a, then we know that the remainder we're going to get is also the same thing as just evaluating the function at that number. It's actually very helpful, right? So if we can take this function and just evaluate it at a, then the number we get is the same thing as the remainder when we divide the function by this term. That means that if this is a factor, right, then if we plug a into that function, we should get a 0, right? Because if this is a term and you plug in a for x, one of your terms is going to be 0. And so that's how we can see that it works when it's an actual factor, but it also works for any remainder. All right, here's an example. If we want to find the remainder of this polynomial when it's divided by x minus 1, we just plug 1 into that function. Right? So you plug in 1 for all the x's. Very simply, you just get all the coefficients, you add them all together, and you get -2, and that tells us the remainder is -2. All right, well, what else can this do for us? Well, if we plug in -3 into this function, we get 6. So now we know that the remainder is 6. We could also do synthetic division with this polynomial, right? And because we're doing f of -3, that means this is all based on the term. This is all based on the term x plus 3. Remember, because it's x minus a. And then when we have this, remember when we do synthetic division, it's always of the form x minus c. So this is x minus a minus 3, and that's why we still use a -3 here. But either way, whether you just plug it in or actually divide by this term and look at the remainder, you get the same thing as 6. So we're just pointing out that the remainder, right, and f of a, same thing. All right, so we now know that our polynomial has this as a factor if and only if f of a equals 0, because that means the remainder is 0. So we're tying those two things together and saying that we can use this as a way to figure out where our factors are, because we can chase these things down. If we plug in some a into the function and we get like a positive number, then we plug in another number and we get a negative number, then we know somewhere in between there is a number that's going to give us a 0, and that's going to be where we're going to have that factor, right? So for instance, we have some function, we plug in 2 and we get like 7. Then we plug in 3 and we get -4. Well, as long as our function is continuous, and if we're talking about polynomial functions, which we are, right, then they're always continuous, and so there's no breaks in it. So if it goes from a positive to a negative, somewhere between it had to have a 0. So that means somewhere in between here, there has to be an f of something that when you plug it in, you get a 0. And that means that there's going to be some factor, and this a is just going to be somewhere between 2 and 3 according to this information. Okay, so that's how we're using this idea to kind of help us. So here's another example. Given that 2 is a 0 of this function, solve the polynomial equation where you set it equal to 0. Well, since 2 is a 0 of this function, we know that plugging 2 into it equals 0, and we know that x minus 2 is a factor, so we can use synthetic division and just do our simple synthetic. Remember, if you don't remember this, we'll refresh your memory. You bring the first number down, then it's multiply and then add. Multiply and then add. Multiply and add, and again, there is our 0. So now, Since the remainder is 0, we know that this original polynomial is going to be x minus 2 times some other piece. And where did this come from? Well, it comes from these numbers here, 3, 8, and negative 3. When you do synthetic division, 3, 8, and negative 3. To find the rest of the zeros, now all we have to do is factor this, and this is a quadratic, and you should be very good at factoring quadratics, right? The first thing you try is just a simple factoring where you know that these two numbers here have to multiply to be 3x squared, so it's got to be a 3x and x, and then these two numbers here have to multiply to the last number, right? So I'll do that in colors. This times this has to give you this piece. And this times this has to give you that piece. And since those are both primes, right, 3 and 3, you're very limited on the numbers. This could have been a 3 here and a 1 there. So you just kind of hunt and peck until you get the ones that work. And if they don't work, then you can go right to the quadratic formula. So using the factor theorem, we were able to find the other two factors, and we were able to find all of the zeros for that function. And it's very important to find zeros. Finding zeros is a very important thing. We need to be able to do that. We're always concerned with when functions are equal to 0. So that's really the why do we bother of this thing. Okay, one other example. Here's our friend a word problem. So the combined petroleum consumption C in quads by a group of the most economically developed countries in the world during 1996-2011 can be modeled by this ugly looking function, but it's still just a polynomial function. Even with all of these horrible decimals, it's still just a simple polynomial. X equals 0 represents the year 1996, x equals 1 is 1997, so basically x just represents the number of years past 1996. That's a very common thing to do with functions that model something over time. Now, the model indicates that if you plug a 5 into here, you get 238 quads of petroleum. And if you don't believe me, you can go ahead and plug it in yourself and do the math and see that if you plug in a 5, you get 238. And that means 5 years past 1996, that was 2001, that's how much was consumed in 2001. Now they want us to find another year between 2001 and 2011 where we also got this output of 238. Now you could graph this and try and kind of figure out where it has a height close to 238, or you could basically set it equal to 238 and solve. And when you set it equal to 238, right, you have this function f of x equal to 38, and you solve. Well, the first thing you do is you bring it over here and set it equal to 0, because we can only solve polynomials set equal to 0, and that's what happened here. And then that's what this is. If you take the original function and subtract 238 from it, all that happens is this last constant changes. So now we have a seemingly new polynomial, but it's still basically from the last one. And we now know that this polynomial is divisible by 5, because we know that if we plug a 5 in here, it's going to equal 0, because before, when we plugged a 5 in, it equaled 238. And when we subtract 238 from it, it now equals 0. So this now becomes a 0 of this new augmented polynomial. All right, so to find another year between 01 and 11 just requires us to find another 0 of this new polynomial that's between 5 and 15. Now, why is it between 5 and 15? Because x equals 5 is 2011, and x equals 15 is 2001, and x equals 15 is 2011. So now, if we take this function and divide it by x minus 5, we get this new function here. Well, how did we do that? Again, probably the easiest way would have been synthetic division. You would set up 0.021, negative 0.973, 11.347, and negative 35. I ran out of room. And since this is x minus 5, right, you're using 5. Bring down the 0.021, multiply, add, da, 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 and you would have gotten a remainder of 0. And then the numbers down here would be these three coefficients, and that would give you your new polynomial. Now to find the zeros of this polynomial, we can't factor it, so we have to use the quadratic formula, which is what we're doing here. And using the quadratic formula, you get two options, either 11 or 30 and a third. But only 11 is between 5 and 15, right? 30 and a third is too far in the future. Right? That's because remember this corresponds to years. So that means it's 11 years. You do 11 plus the 1996. That gives you 2007, and that tells you that's the other year where they had that petroleum consumption. Now I know I didn't show a lot of work in this, but this is just, I wanted to highlight that there is a usefulness to this idea of the factoring theorem and finding zeros.